Yeah, so thank you very much, sir. I hope my screen is visible and I am
Yes, sir.
audible.
Yes, sir.
Okay.
Yes, sir. Absolutely.
In this particular session, we are going to see explaining CNNs, where visualization is one of the major technique for explaining CNNs. So, a very good evening to all the attendees also, and welcome to this particular session. So, here is the outline. First, we are going to see some of the visualization technique and methods like visualizing the filters and kernels. I hope now you are well aware with the convolutional neural network because we are going to talk about visualization of the CNN itself, and then visualize the representation space, which is the last layer, and how we can visualize the activations, means intermediate features, and visualize maximally activating image patches and occlusal visualization. Beyond that, we will also touch upon some early methods of the explainability, means back propagation to the image, visualizing the data gradient, and image reconstruction from latent representation, and guided back propagation, which is going to be connected to something very famous explaining methods that is called CAM, class activation maps, gradient weighted CAM, which is GradCAM, guided GradCAM, and GradCAM++. So these are the basically outlines. We will try to touch upon all these topics in this particular session. So regarding visualization methods, now as mentioned, we can first try to visualize the first layer itself. First layer means what? If we have a convolutional neural network, we have series of the layers which may include convolution layers, max pooling, non-linearity, batch normalization, dropout, fully connected layers. All these layers are going to be arranged in a sequential fashion. So, and usually the first layer that we have is a convolutional layer. If it is a convolutional layer, then we have some filters, and those filters are having some dimensionality. And then we can try it up once training is performed. So whatever we are right now talking, training is already done. We already have a trained model, and then we want to understand what are there inside these trained models that we are trying to explore. We are trying to understand what sort of features these kernels and the filters have learned from the images. So here is one example, and this particular model is taken from the LXNet. So LXNet is one of the very early convolutional neural network which was proposed in 2012, and the first layer in this LXNet was having the filters of dimensionality 11 cross 11. You can see here, and 3 is the number of channel because it was applied on the image. So the number of channel in the input image was 3. So the 3 channel was there in the filter also. And how many number of filter is the 64 filter. So because the filter dimension is 11 cross 11, so we can also try to, and there are 3 channels that we can try to visualize that filter also like an image, because image is also there having 3 channels, and we are visualizing those images like considering the red, green, and blue channel. Similarly, here also we can consider the first channel of the filter as the red channel, and the second channel as the green, and the third channel as the blue. If we consider like that, then we can also visualize the image, visualize the filter as image. And here we can see in the left hand side. So these are the 64 filters after the visualization, means after the training has been performed. These filters are looking like this in the first layer. If you try to have a closer look by selecting some of these filters here and try to see, then we will find that these filters are actually trying to mimic some sort of visual information which are very primitive, which are very basic information usually present in the image. For example, if you see this particular filter, which is the first filter, it is trying to give more focus to a particular object which is there at the bottom corner here in that particular patch. Yeah, but if you see this particular filter here, then it is trying to give the response for such particular scenario where we have some diagonal things and changes are happening in a diagonal fashion. If you see this particular filter, then here in this particular case, again, this is a diagonal, but that diagonal is going to be spread over multiple pixels. If we see the last one, then the last one is trying to give us the information where the things are changing due to the change in the color. There might be some age, but that age is caused by due to the change in the color, because there is a green color, and then it is suddenly getting changed to a different color. So it means what is happening. So from this visualization, at least we can get some idea about what these filters are trying to learn. at least in the first layer. And why we can visualize the first layer in this way? Because the number of channel in the filter in the first layer itself is 3, because we have 3 channel in the input image. So, and from this visualization, at least we can say some information about what early layer or the first layer trying to learn from our input image. So basically, it is trying to learn some very primitive information that may be in the form of ages, that may be like color, that may be the change in the change in the color, and that may be the due to the corners, or maybe some small, very small portion of the objects which are present inside the image. So, however, is it possible the same technique can be also utilized to visualize the other layers of the filters, other filters of the layers, for example, and even the similar observation is also there for other CNN models. For example, if we also suppose if we also build a ResNet 18 with 64 filters in the first layer, or ResNet 101 with 64 filters, or DenseNet 121 with 64 filters, then also what we find that those filters are also trying to learn very similar characteristics. So that's what is one of the also motivation why the transfer learning is actually able to work in deep learning, because even if we see the different data sets, or even if we see different convolutional neural network, in all these cases, what happens, the early layers tend to learn very primitive, very basic features which are mostly present in all sort of images. That's what we say, that it is actually learning generic features. Okay, can we also try to visualize even the suppose layer 2 weights or layer 3 weights? So for example, here suppose if we consider a network where we have the first layer having 16 filters with 7 cross 7, but layer 2 having 20 filters, but every filter has 16 channel, and then we can visualize, because 16 channel we cannot visualize as an image. We can visualize the image only as a one channel grayscale, or three channel as the color image, but we have 16 channel here because the filter itself was having 16 channel, and the dimension of the filter is 7 cross 7. But what we can do here, we can try to visualize every channel of every filter individually. So that's what is happening here. Then in that case, how many number of visualization we will get? 20 into 16. So it means we are going to get 320 number of images to be visualized of size 7 plus 7. And that's what is the visualization that we could see here. And then what we find in this particular case, because we have too many number of every channel of the filters, and there is no much relevant information that we could actually perceive from these visualizations. Even we can see in layer 3 as well, where we have 20 filters and every filter has 20 number of channels. So 400 number of total these different kernels are there, considering all the filters. And again, in this case also, it is very hard to do any distinguish guessing between different these channels of different filters. So that's where this particular technique is going to work only with the first convolutional layer itself, where we have only 3 channels in the filters. Okay, and obvious, but also we can just try to mimic this particular information with this Gabor-like filter fatigs, where in early days people were trying to use this Gabor-like filter fatigs, where it was trying to basically capture the information of different orientation and magnitude of the gradient in local patches of the image. However, as this particular technique is not going to work well for all the convolutional layers, it is more suited for the first layer itself. But it turns out to be that we can also try to visualize the last layer somehow. And how we can visualize the last layer? So what we can do, for example, suppose if we are trying to classify to C number of classes, then last layer has the C number of neurons. Then we can just simply don't consider the last layer, which is the classification layer. We can take the layer which is immediately before the classification layer. That is called basically the feature layer, through which we are getting the final feature, which is actually given to the classifier, which basically gives the class scores. And if we again talk about the LXNet, so it has 4096 dimensional feature. And then we can try to visualize 4096 dimensional feature. But the question comes, how we can visualize the 4096 dimensional feature? For that, we have different techniques. For example, we can apply the principal component analysis. We can reduce the dimensionality from 4096 to the two dimensionality, and we can try to visualize. But though we can do that, but the PC visualization with two dimension, that is not a very good visualization most of the time, people have found. So there is another technique which is more complex in the nature, and that's called T-distributed stochastic neighbor embedding, that is TSNE visualization, and that is very, very effective in practice. And this visualization also simply projects 4096 dimensional feature into a two-dimensional feature, and then we can after that we can visualize. Then what happens here? Then we take different samples of the different classes and we compute its 4096 dimensional feature, which is all using already trained model, and then we basically project that into two-dimensional feature using t-SNE, and after that we just give the different color coding for these different two-dimensional feature of the different samples of the different classes, and for a particular class we give the same color code. So here we can see in the bottom here. Now if you consider all the samples of my data set, then actually we usually get the distribution of the different classes in this two-dimensional projected space. And that's then what is the significance of this visualization? From this visualization, what we can understood that if the different samples of the same class are very compact, are very near to each other, but the samples of the different classes are very far to each other, then that is going to be very good, because at the end what we want to do with the CNN model is to project my raw data into higher dimensional feature space where the intra-class similarity is going to be increased and inter-class dissimilarity is going to be decreased. That's where we can get the better separability between the different classes, and our decision boundary can be learned in a very good manner by the classifier. So through this visualization, at least we can get to know that whatever CNN model we have, whatever the filters we have in all these CNN models, is it working or is it learning the characteristic respect to the data set that we have, such that in the very high dimension, in the abstract space, this is going to basically just minimize, just reduce the similarity, just reduce the just increase the similarity between the samples of the same classes and increase the dissimilarity between the samples of the different classes. So that's how we can visualize basically these latter layers. And this is also going to be useful when we just try to take all the samples, and then based on in what different clusters those samples are going to be categorized. If we just plot those samples in different clusters, then we can also get this particular information, and then in this visualization we find that most of the samples which are very similar in the nature. For example, if we see all these samples where airplanes are there, they are actually going to be very close in the feature space, and that's what we also want, because if they are very close in the feature space, then we can learn a better decision boundary between different classes, and based on that we can have better this classification of the different objects in the data sets that we have. Okay, so early layer means the first layer we can visualize like an image. The last layer we can visualize using t-SNE classifier. But what we could do, which are present in intermediate. So if we talk about the intermediate layers, then what we can do, we can visualize its activations. And when we are going to visualize its activation, we can visualize that as a grayscale image. And in that particular case, what we can interpret, because these are going to be basically the output of the convolutional filters, and we know that convolutional filters are going to give us the high response if it is if it is finding the similar information in a particular region of the image. That's what it actually looks for. So if it happens, then actually it gives us the a higher response. Higher response means the response towards 1. Lower response means the response towards 0. So here we can see one of the example when an image is given to the already trained this convolutional neural network, and suppose when these two persons are present, and if we just take a particular filter on the convolutional 3 output, then what we find that basically this particular filter is sensitive, or this particular filter has learned the information about how many number of people are present in this particular image. So based on that, wherever it finds the face in that particular region, it gives the better higher response, and in other region it gives the lower response. So somewhere different filters in different convolutional neural network tend to learn the different characteristics from the images at a different level of abstractness. For example, if you see the con5 feature, and if you take this particular filter, then it is maybe it is trying to learn something about where is the mouth portion in the image. Wherever it finds the mouth portion there, basically it gives the higher response. So through this particular technique, visualizing activation, the different filters of different convolution can be visualized in terms of its output. Means here we are not visualizing the filter. What we are visualizing the output that we get of that particular filter. So that's what we are trying to visualize. So in that output, if something is towards one means the higher response, then we will get white regions. Otherwise, we will get the region which is close to zero. So this is the technique that we can exploit in order to visualize something which is in intermediate step of the convolutional neural network. There is another method which is called the visualization of the maximally activating image passes, and in fact this is very interesting. So what happens in this particular case in the convolutional neural network? What we can do, we can in any given layer we can randomly pick a particular filter here, and or is we can pick a single neuron. Single neuron means in this convolutional neural network, basically a filter is considered as a neuron in this case. So now we can simply consider a filter in this particular scenario or a single neuron, and then what we can try to do then after that, we feed images to the convolutional neural network, different images we continuously feed, and then try to record that for which image we are getting the higher response by this particular neuron. We are only interpreting only this particular neuron which is selected, and then just give different samples and then try to see that for which sample it gives the higher response. And at the same time, we can also get to know that from that particular image for which we are getting the higher response, even what is the region that is corresponding to giving the higher response by this particular neuron, because we can get the receptive field. What is meaning of the receptive field? In order to get a single value in any given particular layer of the convolutional neural network, we can find out very easily that what was the region in the previous layer which was responsible to get this with this a particular value. Why? Because, for example, suppose if we have a convolutional filter of 5 cross 5, then we take 5 cross 5 region also in that particular layer, and then after that we perform the dot product between those regions, that region and the filter of the same dimensionality, and that actually gives a single value in the output. And then if we, for example, if we have this 5 cross 5 region through which we have got this single value, then what is the region, what is the size of the region in the previous layer that was responsible to get this 5 cross 5? If we just backtrace like this, then we can find out what was the region in the image which was actually responsible to get the response by this particular neuron or any given particular filter. So in this case, now this is a very simple idea and model is already trained, but what we are doing, we are selecting a particular filter and then we are feeding different images and then seeing that this particular filter is giving the higher response for what are the images for which we are getting higher response by any given filter, and then even in that image, what is the region that is actually responsible for that, and that basically can be visualized here. For example, here we can see if we pick a particular filter here, then what we found, what is noticed that it was giving higher response whenever it was finding a face, human face in the image. And there was another filter, it was basically giving the higher response whenever it was finding a dog face in the image. Obviously, sometimes there are some misinterpretation also. Maybe model is not properly trained for such classes. That's why this is happening. And here we can see in this particular case, now it is basically looking for a different object, but the same object, a similar object in all different samples. And now even the last one we can see. Now if we see the last one, now if we see this particular filter, this was actually sensitive to what information? Now if you see this is a face, but this is some different object, again these are a different object, this is face, but what is common across all these objects that we can see in the last row is the reflection. So there is a reflection here in every sample, there is a reflection. So it means this particular filter was actually sensitive to the reflection present in the image. So wherever it finds the reflection in the image, it was actually giving the higher response. So somehow it was basically encoding the reflection information. Similarly, if we take if you take any filter which are present in some early layers, then what we have noticed that in that particular case it was actually giving us the higher response based on some object, but only a portion of a smaller portion of the object. For example, here we can see the first neuron which was trying to give the higher response. Here in this case, this was basically giving higher response due to some specific portion of the dog, either this is the mouth area or this is the eye area. Due to only these areas, it was actually giving the higher response. But if we see some of the filter which was taken from some later layer of the convolutional neural network, then it was actually responsible for even the more information from the image. For example, this entire face is coming here, or the entire dog face is coming in this particular scenario. And why it is happening? Because if it is towards the latter side of the convolutional neural network, by that time, if we basically find out it's a receptive field, then it would be covering the larger area in the input image as compared to the filters with the uh, filters which are basically present in the early layers. Those receptive field, due to those filters, would be very smaller. So that would be actually capturing the portion of the objects, but the latter layers would be capturing even the larger portion, and the last layer finally would be actually capturing the entire global context. So that's where now what we can actually conclude from these type of visualization experiments, that the early layer tend to learn generic features and basically the part-based features, and then those generic and part-based features are getting combined over the layers, and at the end, whatever final features we are getting, those are holistic, those are very abstract, and those are very problem dependent, that what problem we are solving. So it is actually having more context involvement there. So this is one of the important observation from these experiments. However, there is one more visualization experiment that people tends to do, is the occlusion experiment. And in the occlusion experiments, what we do, uh, for the training image, we already know that for this particular sample belongs to which class. Then what we do, we just give that image as the input. We get a class score for the correct class. Now, after that, what we do, we take a mask, we apply the mask at the left and right corner, sorry, left and top corner, and then try to find out what is the class score now for the correct class. And then basically just shift that mask by 1 pixel in the right direction. Again, feed that image with the mask to the CNN, and again let's try to find out what is the class score that we have. So now in this particular case, what happens if we just move this particular mask at different location in the image, then due to that, it is possible that sometimes due to the positioning of a particular mask, the class score for correct class can be drastically down. For example, here in the first case, when this mask is going to overlap with the face of this particular this Pomeranian, which is the true label here, then in that particular case, what we can find here, the right side is actually the map of the class score when the mask is at different places. So wherever we find something which is towards the basically the blue side, it means the class score is going to be basically smaller in that case. However, something which is towards the red side, the class score is going to be higher. It means what? It means when mask was present in the background, then there was no much change in the mask in the class score. But when mask was present at the when it was on top of the basically the this face region of this particular object, then at that time the class score was drastically down. It means it gives us the information about which portion of the image is important with respect to that category, because when your mask is on top of that portion which are responsible, then suddenly your class score is going to be down. And in fact, it was also noted that when there is multiple objects present in the image, then also it is able to learn that which objects belong, which region of the image belongs to which object very accurately. For example, we can see the last example. Here in the last example, the true label is basically the Afghan, this hawk. And what we can see, in spite of even these humans present in this image, when this mask is overlapped with this particular Afghan hound, in that particular case, the class score was drastically down as compared to other areas. It means that somewhere the convolutional neural network is also learning correctly that which region in the image is actually belong to which particular object. Basically, That is a very nice example of basically the grounding of the object. Okay, so all these are basically the visualization methods and also termed as a don't disturb the model method. Why don't disturb the model method? Because the model is already trained and we are not going to change any parameter value of the model. We are simply just using those parameter values just to do the visualization of either the early layers or visualization of the last visualization of any middle layer in terms of visualizing patches that maximally activate the neuron, or visualization of the fully connected layer in terms of the Tishni visualization, or even we can have the occlusion experiments where also we have simply used the model and we have not changed anything. So with the summary of all these methods here, we can see these are simple visualization methods where there is no changes done in the parameter values. Simply the trained values are utilized, and based on that, even we can get a lot of information about the working mechanism of the CNN and what CNN is doing, that we can interpret from these visualizations. Okay, there are a few other methods for the explainability of the convolutional neural network. Explainability means CNN is giving some output, why it is giving that output, that we try to understand. That is basically the explainability. So there are some methods, some early methods that we are going to see for the explainability. However, before going to see these early methods, if anyone has any doubt or any question in visualization methods, you can feel free to ask. So it seems there is some question here. Uh, Here reflection means what? Reflection means, suppose if you have a glassy paper and even if you take the image from your camera, you will find there is a reflection in the image. So there is a question by Pooja here. Let's say I am using unit for segmentation. Now I want to extract features from this model so that I can apply feature selection technique and then classification, which layer is feasible to extract features like last encoded layer or bottleneck layer or early decoded layer, or how to decide. Very nice question. And we are going to see one of the visualization methods of the data gradient. And after that, you will get basically your answer there very accurately, where that data gradient will be utilized. And even you can use that data gradient to have the better segmentation of your model itself. T-SNE is known for visual ambiguity and should not be used as the validation technique for classification quality. Sir, is it true and should not be used in paper? I think that's not very true. If you see the top quality research papers, which is published by the top researchers at the top venues, this T-SNE visualization is very frequently used. Though there could be visual ambiguity, but even that visual ambiguity is not going to basically much deciding factor in terms of the separability, in terms of the compactness of the distribution of uh, these features that we are getting. So that's where, though it has some drawback, because anyway we are projecting 4096 dimensional features into a two-dimensional space. So ambiguity is anyway it is going to be there. But in that case also it is also deciding that what are the different basically dimensionality which are going to have more and more influence, and based on that basically it is a combination which is going to decide what could be the two best dimensionality which can represent those feature vector of even higher dimensionality. There is another question. Please repeat the receptive field. Okay, what is the receptive field? So suppose if you are having your first convolutional layer, and in the first convolutional layer, your filter dimension is 11 cross 11. Then what will happen if we apply that on our image? Then we take 11 cross 11 region from the image and we have the filter, and then we apply that filter on that region, means kind of a dot product that gives us the single value in the output. So in that case, what happens? The receptive field of that particular filter means the single value that we have got as the output by that filter, receptive field of that particular neuron or the filter is basically 11 cross 11. But what happens, suppose the next filter, suppose next layer that we have there, we have again 11 cross 11 filter. Then in that case, what happens now? From if we take the output of the first layer, then from that output, if we take 11 cross 11 region, that is going to give us a single value in its output. But in order to get this 11 cross 11 region, what is going to be this the region size which is responsible to get the 11 cross 11 region in the first layer itself. So that's what, if we consider, that is going to be the receptive field uh, of that particular output which we have got in the second layer. Okay, so there is a Vinod Kumar Chauhan from my side. Reflection means electromagnetic energy that are recorded in numeric value of band. Okay, right now because we are basically focusing in case of the deep learning, we consider image just simply as the data. In that data, we just try to see the pattern. In that pattern, if there is something which is going to be very bright suddenly and just kind of a patch, very brightness patch, that's what is actually going to be considered as the reflection in this scenario. Maybe reflection, that's what we are trying to interpret. Maybe CNN might not be saying that this is a reflection. CNN might be just saying that this is kind of a pattern which is occurring in different images which are having basically this particular pattern, this particular basically the local, or we can say the visual appearance where there is some brightness, and that's what is the reflection that we can interpret. Okay, so now let's move forward. So another type of methods that we are going to see is the back propagation to image, because now we are going to make use of some of the information of the gradient also that we have, that with that we can have in any convolutional neural network. So the question is, can we find out an image that maximizes some of the class score? So that's what we are going to be interested now. Means what could be the image that maximizes some of the class score? So can we generate such type of image itself? That's what we are going to do. So what we do in this particular case, we start with a zero image. Now we have a blank image which has all the values zero, and then we give as the input to our already trained convolutional neural network. And then after that, what we do, obviously we will get the class score with respect to the correct class, whatever class we are aiming for. And then we perform the back propagation by having the objective function to maximize the class score for that class. But in that back propagation, we are not going to change, not going to update the parameters. Parameters will remain same. What we do, we just do the back propagation of the gradient, and finally we compute the gradient of our objective function with respect to this image itself. Because image is also one of the input to this particular function, then even we can compute the gradient of our objective function with respect to image also. Then after that, what we do, we update the image itself. And because this is a maximization problem where we actually try to maximize the class score for any given class, and then in that case, this image that we are going to update will be updated using gradient ascent method, uh, where this gradient is going to be added in, the weighted gradient is going to be added in the image itself. And then we basically do the, first we do the forward pass, and then we do the backward pass. We compute the gradient of our objective function with respect to image itself, and then we add those gradient in the image. And if we repeat this process, and basically this is the optimization. Obviously we need some regularization also. So here is the regularization which is actually used, that is based on the values of this image itself, that because we do not want that some of the values is very high and some of the values are very low. So we want it, basically the values should be in a proper range. So that's where we can have the regularization also. And if we perform that, then what we find here, in that case, we can find the images that are maximizing the sum of the class score. For example, if you see the washing machine, then if this image is given to the trained CNN, then the class score for the washing machine is very high. And for example, if this image is given, then class score for computer keyboard is also very high. Now we can see then what actually we are having. Now we can see if the class score for washing machine is very high when this left and top image is given as the input, then in that case we can also even visualize there are several washing machine kind of a pattern inside these images. And why there are several such patterns? Why it could be there? Because in the data set it is possible that washing, when we have the samples of the washing machine, then those samples of the washing machine are not exactly at any given region in the image, rather it might be at any place in the image. So that's where we could get the translation effect. And that's where what we can observe, that even several washing machine kind of a pattern we can see in the image which are actually maximizing. Even the similar kind of thing we can also see in other images as well. For example, this is goose. Now we can see there are several goose like patterns in this image which are actually maximizing the class score for the goose. So now, again, this gives us the very important visualization information that that convolutional neural network is somewhere actually learning what is basically the shape of the object, what is the texture in the object. Somewhere it is learning the template of those particular information. Okay, so such optimization can in fact be done even for arbitrary neurons in the network. Right now we have done the maximization of the class score, but even we can also try to find out that what could be the image which can maximize even a particular neuron, a particular filter in our convolutional neural network. In that case, what we can do, we can just do the forward pass only up to that neuron, and then in that particular layer set the gradient for all other neurons to 0 and the gradient of only that neuron to 1, and then after that we can just perform the back propagation. If we do that, means suppose if my neuron is suppose in the second layer, then I will do the forward pass only up to the second layer. We will not go beyond that. And in that layer also, what we do, we just set the gradient for all the neurons to 0 except the one that we are actually interpreting. And then after that, from there we just start doing the back propagation, and then basically just generate the image. That's what the experiment we this experiment we can extend with any particular neuron. Another important thing, there was one question about the segmentation that you can correlate here in a better way. So even we can also visualize the data gradient. So data gradient means what? The gradient that we are receiving with respect to the image itself, we can try to visualize, and that also gives some important information. So here, what happens, because we have the multiple channels in the image, red, green, and blue, three channels, then in the gradient also we get the three gradient, because the size of the dimensionality of the gradient that we receive and the dimensionality of the input is same, because the gradient we receive for every parameters and the number of parameters is also going to be the same with respect to what window we have selected. So based on that, because that's the in the CNN we repeat that window for every spatial resolution by sliding. So eventually we get the even gradient for every pixel here. So if we get the gradient for every pixel, and that too we get for every channel of the weight matrices that we have. So what we can do while visualizing the data gradient is to take the maximum of that across the channel. So if we do that, then at each pixel, we take the absolute value and pick the maximum across channel. And that's what we try to visualize. So here we can see this visualization. For example, in this image now, where is the dog? So what happens when we do the back propagation of the gradient? Then we find that the gradient which are corresponding to the pixels which is belonging to that particular object, we are getting the higher gradient there. And for other regions of the image, the gradient is very small. Means the magnitude of the gradient is very small, and that is again going to be very much explainable in this particular sense that the CNN is actually learning the relevant information from the image, and the region which are responsible to get the higher response or the higher class score for that particular category, actually from those regions are given more importance, and for that basically we are receiving the higher gradient. Then how this is going to be useful for the segmentation? So what we can do, so suppose if we have an image and we want to perform segmentation of the object in that image, then we can pass that image to this particular CNN and compute the data gradient with respect to that image. And once we have the data gradient, then the portion where we are getting the higher data gradient, those portions only can be considered to just extract the foreground of means the object from that particular image, and where we have very small gradient means we can just do the thresholding of this data gradient, and after that the region where we get the higher data gradient, entire that region we can consider as a foreground, and remaining region we can consider as the background, and based on that we can basically do the segmentation. And in fact, here is one example where this is done with the graph cut. So graph cut is one of the segmentation technique, and if we just use this particular method with the graph cut, then even we can improve its performance. And even this could be also a good explainability also from the segmentation point of view. In fact, if here we can see in this particular example, there is a lot of clutter here. So due to that clutter, even if we see the data gradient, Then if you try to visualize the data gradient and try to find out the region where we have the dense data gradient. So this region is where we have the dense data gradient, and due to that, basically we can easily find out the object which is of the interest. We can also reconstruct given the latent representation. It means what? We have an image. We pass that image to already trained model and get the latent space, means the output of this last dense layer, which is 4096 dimensional. Then after that, what we do? Now we basically, now after that, uh, once we have already got this 4096 dimensional feature for any given original input, then after that again we start with the zero image and then get this 4096 dimensional feature itself, and then try to minimize the distance between the 4096 dimensional feature that we have got for any blank image and that we actually got for any given image. And then after that we compute the gradient, and that due to that gradient we are going to update the blank image. And if we basically do that, then we can reconstruct the image which are responsible to give the similar type of 4096 dimensional feature that we actually got using some original image. Here we can see, so the first diagram here was the original image. Due to that we have got some 4096 dimensional feature. Now we are getting basically these blank images, and then after that uh, we are getting the same 4096 dimensional feature and then computing the distance and then trying to minimize that distance. That's what becomes the objective function. So that's what is the objective function here. This phi x minus phi naught means minimization of the distance between the features of that 4096 dimensional, plus there is some regularization of that image itself that we are actually reconstructing. So due to that, here we can see whatever image which is being reconstructed, they are also getting some sort of similar visual appearance that was actually present in the original image. It means that if we are getting some feature dimension, if we are getting some feature vector at the end of the convolutional neural network, then that feature vector somewhere has the information or whatever is a global perspective of the objects which are present in the image are actually well coded in that 4096 dimensional feature also. If it is not done, then in that case we would not be able to reconstruct the image by just using those 4096 dimension feature. But here, because we are able to reconstruct the similar appearance, it means that the CNN was actually able to get the context of the global representation of the object. So that's what is the explainability that we could get from this particular experiments. And even not just the last 4096 dimensional feature, even we can take the features which was just before the fully connected layer, and we can even just try to minimize the distance in that feature itself, and that is also going to work well. Now, leading to another method which is called the guided backpropagation, or also known as deconvolutional method, which is very commonly used, which was proposed in 2015. And in this method, what we do, we take an image, now we give it to the already trained convolutional neural network. After that, what we do, we pick a particular layer, and in that particular layer, we set the gradient 0, except for the neuron of the interest. It means we pick a particular neuron and we just want to basically interpret that neuron. So in that layer, we set the gradient 0 to other neurons, and only for that neuron, we have the gradient. And then after that, we do the backward pass. And after doing the backward pass, what we can do, if we do the backward pass, then in that case, we can basically just get the image which was basically responsible to have the higher response here. But while we are performing the backward pass, because here is the ReLU activation function which is also being used. So what happens in any given layer, due to the ReLU activation function, when the negative values were converted into the 0, during backpropagation, what we do, corresponding to those negative values, even though we receive the gradient, those gradient will be converted to 0. For example, here, due to these particular pixels where -1, -5, -1, -3, due to these four, the ReLU activation actually converted them to 0. So during back propagation also, what we do, whatever gradient we have got with respect to these pixels, we have converted them to 0. So that's what is here. So this RIL is equals to FIL. So FI is actually based on the original features that we have. However, R is based on the gradient that we have. So we consider all the gradient, but in that gradient we multiply wherever the feature was greater than 0, only those features are going to be considered in the gradient also. So, but if we apply this particular method, so what happens, the kind of a visualization that we get on the images, that visualization is not very good, or not very attractive, or not having very relevant information. And the reason why it doesn't have much relevant information, because there is a negative gradient also present in this gradient that we are actually visualizing. So what happens here, this guided back propagation, because it has this particular issue. So in the guided back propagation, usually the final guided track propagation that we have there, we also convert all the gradient which are negative, those gradients are also converted to 0. It means that we have got the gradient, but in that gradient, all the gradient which are negative is converted to 0, and all the gradient for and all the features that was negative, and due to that ReLU converted them to 0, corresponding to those pixels also we are going to convert their gradient 0. It means the where ReLU converted negative values to 0, corresponding to that, either it is positive gradient or in negative gradient, irrespective of that, it will be converted to 0. And for other pixels, wherever the gradient is also 0, that is also going to be converted negative, that is also going to be converted to 0. If we do that, then after that, whatever visualization we get is very, very nice visualization, and where we see very important regions of the image which are positively related to the response, high response that we are getting here. Because so why we are converting the negative gradient 0, because that gives us the negative correlation, and then we want to just, and that negative correlation is actually giving us the noise. So we just want to get rid of that noise in the visualization by throwing away the negative gradients, as well as the gradient due to the negative values in the feature also. So both are converted 0. Then basically only those regions which are positively related to the in terms of the feature also, and in terms of the gradient also, to any given particular neuron, that's what we can simply visualize here. So this basically gives us the good interpretability that a particular neuron is actually looking for what sort of actual information from the image. So this was the second type of methods that we have seen. Now another type of methods which are very recently used, that is based on the GradCam and all. That's what we are going to see next. But again, in between, if there are any questions that we can take. So let's see if there are any further questions here. So once tell about data gradient and how this will affect. I think that is already taken. So in case there is no question here, so let's move forward. Then we can take the questions at the end. Okay, so now another type of method is class attribution map methods, which is called the CAM. So what we have seen so far, basically the don't disturb model, as well as the gradient based visualization based models. Now we are going beyond optimization to image methods, and in that now what we are going to look for, basically what a network is actually looking while it is predicting a class. When it is predicting a class, then from class score what information we can get about basically the network. That's what we are interested to now see. So a method which was proposed in 2016, that is called class activation map, that is CAM, which is very famous. So in this class activation map, what we do, we already have a trained model. In that trained model, what we do, we basically just remove all the fully connected layers. Whatever fully connected layers we have, simply remove all the fully connected layers. Then we take the last convolution layer that we have, and then last convolution layer, all the channels of the last convolution layer, we perform the global pooling on that. So suppose if we have C number of channel in the last convolution layer, then basically we get C number of values after the global pooling of the each channel. And then after that, we basically have a fully connected layer here. A new fully connected layer is added here, which is going to compute the class score for different classes. So how many number of neurons are there? That depends upon how many number of classes we have. And how many number of values we get after global average scoring, that depends upon how many number of channels we have in this activation which we are getting after the last convolutional layer. So what then after that, what we do, basically we perform the training of this last layer which is added here. It means now training is also involved. The model was already trained, but we are not going to change the weights of all these convolutional layers that we have. Those will remain frozen. only the weights of this last layer which is added here is going to be trained. So in that case, these weights W1, W2, Wn, all these are going to be changed such that we are actually trying to maximize the class score for the correct class. Then once this added layer has been also trained, after that what is happened, the weights that we have learned here like W1, W2, W3 and all it. So these weights, using these weights, we are going to basically combine whatever is the activations that we have got here. So these activations are going to be multiplied. Uh, 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 these activations are going to be multiplied with the weights that we have, and then that basically gives us the final class activation map. And this class activation map we can basically visualize by superimposing on the image, and that basically gives us the information about wherever we are getting the red area inside that. It means that that is of the most importance. More towards red is more important. More towards uh, this blue side is less importance for that particular disease. Why? If you see this image, in this image, the class of this image is this Australian Terrier. It means it is actually focusing on basically this particular offset. This is whatever is the Australian Terrier, not the person here. That's what is also confirmed by this saliency map that we are getting due to this class activation map visualization. So here we can see a few more examples. For example, here, if we take this particular image, and if this particular image, this is blurred, so this is actually giving us more importance, more saliency on this particular facial area here. And in fact, here now, if you see, this is very interesting image, the fourth one, where this image is getting classified into barbell, which is actually kind of a dumbbell, which with this person is actually lifting. And because this image, the class activation map is maximized with respect to the barbell category, so actually it has learned where to give more focus is actually this disk which is being used here. So actually it is learning the context very well about different objects that we have. It means somewhere CNN is actually going to learn the object level information very well. Means the locality is going to be very, very important, and using locality, it also learns the global context. How we can say it learns the global context also. If we take an example here and try to do the visualization with respect to what are the portion of the images which are responsible to give us to get the top 5 classes score for different classes. So here if we see that the topmost class is the palace, and for that this entire region here is actually responsible in this case. But if you see the second class for which we have got the second highest class score, that is 0.195, if you see that was the dome. And in fact, through this visualization also it is confirmed that when this dome was considered as the second class score, then in that case the features of from the image region which was actually more responsible to get these classes scores are the dome area. So in fact, in other cases also we can find the similar cases like church. So it is covering basically this frontal part which is looking like a church, though it is not a church but looking like a church. This altar, so somewhere it is looking like this gate information in giving more importance. This monastery again, this entire this frontal region is giving more importance because it also looks like a monastery. Okay. So here is the intuition of the CAM. Convolutional units we have as a object localizers even without supervision over the object location, and this capability is lost if fully connected layers are used for classification. So that's where basically even if we have less number of fully connected layer but more number of convolutional layer, that is even going to be in a good choice. And that's what happens even in if you see the neural network, or even the Google net, there the number of fully connected layers is minimized, because if we use more fully connected layers, somewhere we are going to lose the locality. So this is the comparison again for different examples here. Now, if you see the advantage of this class attribution map, uh, it is basically class discriminative, that is very well, and doesn't require any backward pass through the entire network, which was required by the guided backpropagation here. In this case, the backpropagation was required only for the last added layer. However, what is the disadvantage? There is a constraint on architecture is restrictive, and we can only perform for the classification because we can only maximize the classes score here, and we have to do the retraining. That is another kind of a drawback here, and model with trade-off accuracy for the interpretability. That is another case. So these problems are actually resolved in another method which is called GradCam, gradient weighted this class attribution map. In that case, and what is one of the important thing in case of the GradCam, we need not to remove any layer, we need not to add any layer. Whatever is the original convolutional neural network we have, which is already trained, exactly same thing we are going to just utilize here. So what we do in this particular case, we take the last convolutional layer of the CNN, and then we just do the back propagation of the gradient, and we get the gradient with respect to all the channels that we have in the last convolutional layer here. Then after that, we get the gradient channel for every channel of the corresponding layer, and then we take the global average pooling of those gradients. Then after performing the global average pooling of different channel of the gradient, we get the weights, and that weight is actually used to combine the features that we have here in that convolutional layer, and that's what actually gives us the better visualization, which is called the graph cam. So here we can see, now we can see this grad cam is, and on top of that ReLU is applied. It means the negative values will be converted into zeros. And basically this is some summation of this alpha kc multiplied over ak. So ak is basically the features that we have here, and alpha is actually the global average pooling of the gradient, because this alpha is computed as del y, means this is just global average pooling over del y by del a, which is nothing but the gradient. So it means what? This is a very simple technique where whatever features we are getting at the end of the last convolutional layer, corresponding to those features, we are also computing the gradient. And then we take the global average pooling of those gradients, and those global average pooling will serve as a weight. Using that weight, we combine those features itself. And then whatever we get is actually passed to the ReLU, rectified linear unit, and that is actually the saliency map that we get for the visualization purpose here. So here we can see this is for the tiger cat in this example. So now even we have the we have this dog also, we have the cat also, and in that case, wherever the tiger cat is present, it is giving more importance to the matrix here. Also having some importance can be also highlighted. But if we combine both, then in that case, even we can get the better visualization in terms of that what are the gradient also from the images, which is going to be better utilized. So the advantage of the grad cam is it doesn't need the uh,
Sir, your
this.
screen is not visible.
Sorry.
Can you please reshare, sir? Can you please reshare your screen, sir? It is not visible.
Oh, sorry for that.
No
I hope
problem.
now it is visible.
Yes, sir. Yes, sir. It's visible, sir.
Okay. So what I was just explaining before. So this was the grad cam that we have seen. So in case of the grad cam, we got the visualization. So we can get the another version, which is the guided grad cam. So in this case, whatever guided back propagation we have seen, so we get the output of the guided back propagation, we get the output of the grad cam, and then we can just multiply both. If you multiply both, then what happens? Where grad cam is not able to give the focus, in that case, the output of the guided back propagation is also going to be converted towards zero. So in that case, even we can get the better interpretability that why this particular image was classified into the tiger cat category. Okay, and another important thing about the GradCam is we need not to change the architecture of the this convolutional neural network. So in that case, even it can work with for different problems also. Like it can work the image classification also. Even it can work for the image captioning also. It can work for the visual questioning answer also, and even for any other application also it can work. And we also don't have to do any retraining. So that's where this is going to be much better than this simple cam. However, even if we see the GradCam, so GradCam maps, these are the class discriminative, that's very well. However, sometimes it is unclear from this heat map that why the network predicts this particular instance as a tiger cat. So can we do something about this? So in that particular case, what happens in the guided GradCam, what was found that when we apply the guided GradCam, And in that case, if we consider a dog and if we consider a tiger cat, then that's what is the interpretability that we get here. So this is the dog and this is the tiger cat. But in case of the tiger cat, even we get some information about the dog. So whatever was present on the dog, this is also getting somewhere highlighted. Some portion is highlighted as the tiger cat. And what could be the reason for that? So that's where basically the counterfactual explanations can be also performed using GradCam, where what can be done, the weights that we are receiving, the gradient weights, that can be negated here because we are applying ReLU on top of that. So what happens, the something which was negative was discarded earlier now will get selected, something which was positive and discarded earlier will now get selected. So what happens, basically this is simply going to kind of a reverse the effect of plus and minus in the gradient. And due to that, what we can see here, if you see the original image, this is the grad cam for the cat, and this is the grad cam for the dog. So, and this is the grad cam for the negative explanation of the cat. It means, then what is the difference? The difference in the first case, when grad cam was being used, we were trying to find out why these images belong to the cat. Now, what is counterfactual explanation is, why this particular image is uh, this GradCam negative explanation for the cat. It means that what is the reason that a particular what is the reason that the background, due to the background it is actually classified as the cat and the background is not classified as the cat. It means that our other object which are present, why that object is not classified as the cat. For example, in this case, two object is present. So when we are applying the grad cam, and then we are saying that we are applying the grad cam with respect to the cat category, then what we are saying that why this image is classified as the cat, that's what visualization we are getting. Now, if you see the counterfactual explanation, then in that case, what are the other object? Why that object was not classified as a cat? That visualization basically we are getting here due to the counterfactual explanations. However, though we can apply the GradCam, but it was found that the GradCam is having the inability to identify multiple instances of the object. For example, here we can see in this image, though there are several dogs present, but only some two or three instances of the cat was basically figured out by this guided GradCam, and even by the GradCam as well. If you see here in this case, in this case, what happens? If there is some unsatisfactory localization performance due to the occlusion, that may also result some problem in using GradCam. So this particular problem is actually resolved in another method which is called GradCam++. And what GradCam++ tries to do basically is tries to give more importance to basically whatever gradients we are getting for a different size of the object. If the object size is smaller, then the gradient is also smaller. If the gradient size is larger, then the gradient is also larger. And due to that, this GradCam was not able to basically distinguish between different size of the object, there is a occlusion, or there are different instances of the object, and there was a problem. So what this GradCam++ has done, based on the size of the object, actually it has performed the normalization of the gradient also, such that even if for the smaller size, the gradient information is boosted here. For example, here if you see, this is for the smaller size, the gradient was lower, like 0.26 as compared to gradient which is 1.0 for a larger region. In this case, in case of the GradCam++, this is also going to be normalized. That's what was the contribution of this GradCam. And how this is done, so this particular thing is done by having a particular constant included here, which is basically this alpha kc, let's say, in this. That's what we can see. So this was the motivation, and how this is computed. So this is basically computed based on the second order and third order derivatives, which was actually utilized in order to get that. And then at the end, ReLU activation function is also applied in similar way like it was applied in GradCam. And then it was noted that where the GradCam was not able to give more focus, GradCam++ is able to even distinguish better and even capture the different instances of the object very clearly. And even it is able to capture even the clutter also very clearly. And so this GradCam++ now we can consider as the better version of the GradCam. So now if you see here, these are few other examples of GradCam++ for the class localization, and we can see very nice visualizations that we have got in terms of the class importance in that image. There are a few more where multiple appearances are present. So this is still able to do well. So that's all in this particular session, and most of the content in this particular session was taken from NPTEL course, which was by Professor Vineet Balasubramaniam from IIT Hyderabad, which is deep learning for computer vision, and also something is taken from the convolutional neural network for visual recognition, which is very standard course of Stanford University, and some portion is also there from the deep learning course, which was taught by Dr. Mitesh Khapra from IIT Madras. So with this, now this is all about this particular session where we have seen some visualization techniques and some class attribution methods and some gradient back propagation based methods for the visualization and explainability. Now, if you have any questions, you can feel free to ask. There is a one question by Pooja here. Lime and SAP performs better than GradCam. Yeah, obviously, but Lime and SAP, this is going to be even very, very costly because for every example, you have to perform that. And in this case, we are not doing much task here, and still we are getting explainability. So though Lime and SAP, these are a different type of method, so I have not covered here because we have limited time. Maybe in some other session if it could be covered. So there is a question by Pradeep. This GradCam limitation can be overcome. Any suggestion? Yeah, that is already overcome by GradCam++. So in now, suppose if you have to utilize, you can directly use GradCam++. So again, there is a question by Pooja. Let's say I am using unit for segmentation. Now I want to extract features from this model so that I can apply feature selection technique and then classification, which layer is feasible to extract features like last encoder layer or bottleneck layer or early decoder layer, how to decide. Okay. So yeah, this is very nice question. So what you can do in this particular case, the features that you are extracting, because the early layers are extracting very generic features, and because you want to use this for the classification, then in that case you can take the features which are towards a little bit towards the latter side, and even you can take the features of the multiple layers and you can combine, and then you can use those fused features to perform the classification if you want, or you can use that one as basically just to a classifier, and you can train that classifier on top of that. Means the further training of the classifier can also be performed in this particular case. This is one scenario. Another scenario, even the data gradient can be utilized, and using the data gradient, what happens when you are performing the back propagation at that time, whenever you are picking a particular layer and you are taking the feature of that layer, then what you could do one thing, don't take all the features. Then based on the data gradient, wherever you are getting the high gradient, take only corresponding features and just prune other features, set other features to zero. So it means something which was due to the noise or due to the other factor in the image, that particular features are going to be deselected, are going to be basically removed. So that could even do better as compared to considering all the features. So I hope this makes sense to you.
Yeah. Any other queries from participant side?
Okay, how many features should we select? That depends upon your data gradient. So you can basically have a threshold on the data gradient, and you can say that if my data gradient is higher than this threshold, then corresponding to that, whatever features are there, all those features we will select. So you can have a hyperparameter here, and then you can vary that hyperparameter and see what performance you are getting. So there is another question by Vinod Kumar Chauhan. Kindly upload all lecture materials and videos that are completed. Yeah, that organizers will take care of that.
Yes, yes, absolutely.
Uh, can There is a question by Pradeep. Can I mix PCA and LBP, HOC, GLCM? This is already being done. Many people are already doing all these things, and if you want to do that, you're free to do that. Okay, so thank you very much to all the
Yeah.
participants for listening this particular session, and thank you very much to Dr. Deepak also for giving this chance. Maybe if you have any further question, you can write to me. So thank you very much.
Thank you. Thank you so much, sir, for delivering a wonderful lecture and for sparing a valuable time.
Okay, sir. Thank you,
Thank you,
sir.
sir. Thank you, sir.
Bye, sir.
Bye, sir.